Welcome to video 1 on the TTB course. I'm going to begin with some basic background to get us started. There are a very wide range of embedded systems across the planet. By an embedded system, we usually mean some kind of computer-based system that to most users doesn't look like a standard computer. So we have a range of different possibilities indicated on this slide. Our focus on this course is going to be on two broad categories of embedded system. The first category is reliable embedded systems. Everything we'll be discussing on this course is intended to be reliable. One of the primary motivations for creating reliable embedded systems is to avoid the very significant cost of repair or significant costs related to the system failure. For example, if we have a satellite system, the cost of repair is vast. We have to recover the satellite perhaps in order to effect repairs to the system. If we're lucky, we'll be able to upload a new version of software perhaps to our satellite, but if the component that's responsible for uploading the software fails, then we're in trouble. In fintech type systems, financial technology systems, we also have many challenges. Clearly, a failure of this kind of system could prove to be extremely expensive. If all of the auto teller machines, the ATM machines such as the one illustrated on this slide, if these machines fail, we could start handing out free money across the planet. Clearly, that's something that we would generally wish to avoid if we were manufacturing or creating such machines. The next main category and our key focus throughout this course will be on safe embedded systems. So these are the kinds of systems where if they go wrong, someone is likely to be injured or killed. So for example, very simple example, a washing machine. That will be familiar to many people that are joining this course. One of the key safety challenges with such a machine is that if the door lock fails, it's possible to open the door while the machine is spinning a large metal drum at high speed. If you, or particularly a small child, manages to insert his or her arm into that drum while it's rotating rapidly, they could be very badly injured, or in the case of a small child, they may even be killed. In automotive systems, there are many opportunities for failure. Failure of the braking system, failure of the steering system, increasingly a focus on advanced driver assistance systems, adaptive control systems in the car, self-driving systems, self-parking systems. In many of these cases, failure of the system is again likely to cause severe injury or death to passengers, other road users or pedestrians. Again, we need to avoid such problems. So we'll be looking in this course at a range of techniques that will allow us to produce safe and reliable embedded systems. Let's start with some of the key considerations that we're going to have. Timing requirements. This is a key issue in many of the systems that we'll be looking at on this course. So we'll be talking about a category that's usually referred to as real-time systems. You've got the quote on the slide from Wikipedia. More generally, it's simple to summarize the requirements of real-time systems as saying that we're concerned not only with the functional behavior of the system, that is what it does, but we're also concerned at the time at which this activity is carried out. For example, if we have a braking system in a car, we may get a perfect braking response, but if it takes 5 seconds to produce that braking response, we don't care. We'd rather have a less than perfect braking response on time rather than having to wait too long for the perfect response to be created by the system. So time, the time at which outputs are created, in particular inputs are measured, is crucial in many real-time systems that we'll be discussing during the course of this course. Let's look at a couple of examples. This one's straightforward. It's part of the description that might be used in a traffic light system. A green light must be shown to every road for at least 30 seconds in any period of 5 minutes. So this might be used to describe traffic lights at a junction, at a crossroads, where we want to allow traffic from the two crossing roads to have some kind of opportunity to move. We want to avoid jamming up the traffic by ensuring that each part of the crossroads is able to operate as required. Here's another example. This may not at first glance look as though there's a timing requirement here, but usually there is. So this says the control system shall ensure that the fuel temperature does not exceed 120 degrees Celsius. So in this case, where's the timing requirement? Perhaps because we're making periodic measurements of the temperature. If our periodic measurements don't happen when we expect them to, if one timing measurement is very delayed in our system, then we may miss a high temperature value, which happens briefly in the system. If we miss such a value, this may, we assume, be dangerous in this particular application. So sometimes timing requirements are explicit, as in the first case here. Sometimes the timing requirements are implicit, and we have to think about them a little bit more carefully during the system development. Here's another typical timing requirement. In this case, we're looking at response time. In this example, we're saying the brake actuator shall begin to close within an interval of 10 milliseconds after depression of the brake pedal is confirmed. A fairly straightforward response time requirement. We'll say much more about this type of requirement and how we can meet these types of requirements and demonstrate that we've been able to meet these requirements in this course. We might need to respond to errors in the system. Here we're suggesting that we may need to be able to detect the failure of the main pressure sensor in a system within a specified period. And we must be able to engage a backup sensor, again within a predetermined period. Again, we're then looking at internal errors, where any critical task exceeds its predetermined worst-case execution time by more than 2 microseconds, this shall be detected. The overrunning critical task shall be removed from the schedule. The corresponding backup task shall be scheduled as a replacement. Again, we're going to look at mechanisms that would allow us to achieve this later in this course. One of the first basic timing challenges that people come across often is one of CPU loading. Your system may come with a requirement from the customer that the CPU load shall not exceed 50% at any time during normal system operation. In many cases, it's very difficult to guarantee this. We'll look at techniques that allow us to confirm at design time that we'll be able to meet this type of requirement. One of the reasons why this type of requirement is useful is that if we're able to model the system and understand exactly what the CPU loading is, we'll be able to answer questions such as the second one on this slide. So we'll know whether it's possible for us to add another task to our system without having any impact on the existing task set. This is a key requirement in many projects. Very often, additional functionality is added late in the project, We want to be able to avoid having to retest very large parts of the system during the project if we can avoid doing so. The techniques that we'll be discussing on this course will allow us to achieve this. Task jitter is another one of the issues that we're going to consider during this course. Jitter refers to a variation in timing. So for example, in this case, let's assume that this represents a sine wave that we're trying to sample. So we want to sample at the point indicated by the arrow here. Instead, we have a slight variation in the timing at which we sample, delta t here. This gives rise to a small variation in the voltage that we sample that's indicated on the graph. If you have a look at the ERES2 book, and I'll give you a full reference to that book in a minute, you'll see in the appendix of that book, one of the appendices of that book, a demonstration that if we have jitter here of more than approximately 1 microsecond, we'll start losing information even in this very simple sampling task. So we're sampling a 500 Hz tone using an 8-bit ADC, which is a very modest requirement. If we have more than 1 microsecond of jitter, we will not manage to perform this task successfully. Effectively, at around 1 microsecond of jitter, this will become a 7-bit ADC. With a bit more jitter, it becomes a 6-bit ADC, and so on. We need to understand the level of jitter that we're going to see in our system so that we can be sure that this jitter will not be excessive. As a general rule of thumb, jitter levels greater than about 10% in a periodic task means that the data that you're working with are likely to be meaningless. We'll look at techniques that allow us to model the level of jitter in our systems later in this course. So now let's consider briefly, as part of our introduction here to the material that we're going to cover in this course, let's consider some basic safety requirements. So we're going to look at a range of different safety integrity levels during this course. At the basic level, at SIL 0, or in automotive terms QM level, we have very limited safety requirements. At the other end of the scale, at SIL 4, or what is in an aerospace domain level A requirements, we have very severe requirements to meet. So for example, a level A requirement might be applied to the control of aircraft engines in a civilian aircraft. If you're used to working with automotive designs, possibly in compliance with the international standard ISO 26262, which we'll say quite a lot about during this course, the highest standard there is ASO D. There's a level above that that's used in some other standards, but still achieving ASO D, which is roughly equivalent to SIL 3 in the generic IEC 61508 standard, achieving these levels is challenging. We'll look at techniques that allow us to achieve these safety integrity levels during this course. Let's just look at one example of the kind of challenges that we face in a safety-related system. And this is a freedom from interference requirement. Task A and Task B in this design. If you tell me that you've got a design and you can guarantee that Task A won't interfere with Task B, and they both tasks are running on the same microcontroller in a situation like this, if you tell me that's what you've created, I will be skeptical. I won't necessarily entirely believe you. I won't believe that you're necessarily able to achieve that. because there are so many ways in which the tasks can interact with one another. If we can't achieve a guarantee that the tasks cannot interfere with one another, what we may be able to do is to detect that one task has interfered with another task. That's in itself very useful. If we can detect that interference has occurred between tasks on our system, we can often avoid many of the most severe consequences of unintended interference between tasks or other software components that are running on the same processor. We're going to say more about this later in the course. But achieving freedom from interference in this manner, detecting interference between tasks, is another important consideration in many reliable and safety-related systems. So, in this course, we'll be considering a range of safe and reliable embedded systems. We'll need to meet tight timing requirements in some cases, meet the requirements of real-time systems. We'll often need to meet specific safety requirements in compliance with one or more international safety standards. How are we going to achieve this? The focus of this course is on achieving these goals using time-triggered software architectures. As a very brief summary, when we say that an embedded system has a time-triggered architecture, we mean that it executes at least one set of tasks according to a predetermined schedule. The schedule determines the order of the task releases, the time at which each task is released, and whether one task can interrupt or preempt another task. In practice, what this usually means is that we'll use a bare metal software platform for our system. That means no RTOS, no Linux, no Windows. We'll also use just one active interrupt per CPU as a starting point for our design, and this interrupt is usually linked to a periodic timer tick. We're going to poll all the peripherals on our system. So that's a starting point for our system development, and that's how we're going to achieve our safety and reliability requirements on this course. We'll say lots more about time-triggered architectures, what they mean and how they can be implemented throughout the course. One way of viewing what a time-triggered architecture is by considering event-triggered systems. So event-triggered systems, with which many people watching this video will be more familiar, these typically involve, let's say, one microcontroller with multiple interrupt sources enabled. So we might have an interrupt connected to a CAN bus, an interrupt connected to another serial interface, interrupt connected to analog to digital converters, etc. So we have multiple interrupts, different levels of interrupt priority, perhaps a real-time operating system involved. What I'm going to argue on this course is that's a general class of useful systems. TT systems form a safer subset of that kind of system. So what we're describing on this course in many ways isn't new. It's simply saying, okay, multiple interrupts, for example, an RTOS, for example, these are generally fine. There's nothing wrong with these approaches. But if you want safety and reliability, sometimes you have to accept a few constraints on the way that we put the system together. The end result is a TT system, which is going to be the focus of what we discuss during this course. TT systems are widely accepted as being suitable for use in safety-related systems. This is a set of examples that are adapted from the IEC 61508 International Safety Standard. In IEC 61508, TT architectures are highly recommended for systems with a safety integrity level of 2 or above. Static synchronization of access to shared resources, which is a key characteristic of all TT designs, is recommended for SIL3 systems and highly recommended even for the most safety-critical systems that are considered in IEC 61508. Limited use of interrupts, another key defining characteristic of TT designs, is recommended for the lower level systems in IEC 61508 and highly recommended for high level systems in this standard. We'll say lots more about this standard and the ways in which we can meet this standard during the remainder of the course. So, in overview, this course is intended to help you to understand how time-triggered architectures can be used to create safe and reliable embedded systems. During the videos, I'll compare time-triggered and event-triggered solutions. The material that I present is intended to help you think about what will be a new way of developing embedded software for most people that watch these videos. The course is structured around a series of video lectures. You can buy a printed set of the course notes that follow the lectures from our Lulu store. The course also involves guided reading. In particular, the course follows the ERES2 book closely. You'll need a copy of this book to complete the course. I'll say a little more about that book in a few minutes. Overall, most people are expected to be able to complete this course in a period of between 1 to 2 months if they view 1 to 2 videos per day. So what's the best way of preparing for this course? We have a number of free videos available from our TTA introductory course, and you can find these free videos on our website. These videos cover about 7 hours of training and may provide you with a useful background to prepare you for the material that's presented in much greater detail in the present course. I've also written a couple of introductory books that may be useful here. The Patterns for Time-Triggered Embedded Systems book may be particularly useful. So this is available now as a large PDF file, about 1,000 pages. The URL is on the screen. If you wish, you may find it useful to download this book and refer to it as by way of preparation for the present course. I've also written a more introductory book, Embedded C, that may be useful if you find some of the material that's presented in these videos to be challenging. As I've mentioned, this course will follow the ERES2 book closely. The Engineering of Reliable Embedded Systems second edition, details of which are on the screen, will be used as the basis of this course. So essentially what this course does is it follows this book from start to finish. Roughly, very roughly, 1 video on this course per chapter in the book. That's quite deliberate. The idea is that material is presented in the videos. You can read a slightly different interpretation of that material in the book, and overall it should all glue together. And by the end of the course, I hope the key concepts on the use of time-triggered systems to create safe and reliable embedded systems should be clear. That brings us to the end of this first video on the course. To get started with our guided reading, please read the preface, Chapter 1, Chapter 2 and Appendix 1 of the ERES2 book before you view the next video. If you find the material in ERES2 challenging, you may also find it useful to view our TTA videos and take a look at the PTTS book before you continue. I've given information about the TTA videos and PTTS on previous slides in this video. Thank you very much for watching.